All right, so we're going to finish up section 4.2. And as a reminder of what we did yesterday, we did graphing rational functions. And the examples we did yesterday always had the degree of the numerator less than the denominator or equal. So we looked at problems like that. That would be a problem where the degrees in the top are equal. And here's one where the degree in the top is smaller. Okay, those are the two kind of problems we did yesterday. This one always has a horizontal asymptote at what number? Because the degree in the bottom is bigger. It's always going to be at what? 0. This one always has a horizontal asymptote at, well, whatever those two numbers divide out to give you, because the x cubes are gone. Right. Okay, any questions about the kind we did yesterday? All right, so today we're going to look at the kind where the degree in the numerator is bigger than the degree of the denominator. When the degree of the numerator is bigger than the denominator, horizontal asymptotes go away. You can't have horizontal asymptotes. They are replaced by something even more fun than horizontal.
I like the word fun.
But they are replaced by something else. Vertical asymptotes, those are exactly the same. Nothing happens with those. You're still going to find the zeros of the denominator. Okay, but when the degree of the numerator is greater than the degree of the denominator, you will not have horizontal asymptotes. You can still have vertical. Okay, so let's take a look at what happens. What is going to replace the horizontal asymptote is going to be called the end behavior asymptote. We're going to abbreviate that EBA. Not to be confused with the EBM. That's different. Okay, the EBA. So we're still going to look at the same kind of problems that we had yesterday. You're going to have a polynomial in the top, and you're going to have a polynomial in the bottom. So here's an example of a problem, just like that. The only difference today is the degree in the top is bigger than the degree in the bottom. Now, when you divide two polynomials, you get an answer, and your answer has two parts. Does anybody remember what we call the two parts? When you do long division, you get a quotient and a remainder. Yep. So we get a quotient and we get a remainder. I'm going to call the quotient Q of x, and I'll call the remainder R of x. We don't know if the quotient and remainder are just going to be a single number. It depends what you divide. You could get a quotient of like 5, or you could get a quotient of like x plus 7. You can have a variable in the quotient and in the remainder. But you're going to get a quotient and a remainder. So the quotient is the EBA. So finding the EBA isn't really anything new. It's not like something we haven't done before. The quotient is the EBA. Just remember, anytime you write an asymptote, it has to be an equation. So if I ask you for an asymptote and you just tell me a number like 5, that's not an asymptote. It could be y equals 5, x equals 5, but it's got to be an equation. So now when we do the division, you have a couple different ways. Okay, we've talked about long division. Does anybody remember the other method that was shorter?
Synthetic.
Yep, we can use synthetic as long as the denominator is x minus a number. So if we have the opportunity to use synthetic, I'm going to use it because it's faster. Okay, so keep that in mind. That's all you have to do to find the EBA. You do the division, and the quotient is the EBA. That's it. Just make sure you write it as an equation. All right, so let's try finding the quotient, the remainder, and the EBA for example 5. Okay. First of all, does synthetic division apply in this problem?
Yes.
Yes, it does. When I do the synthetic, what number would go on the outside?
2.
2. It's always the number after the minus sign. 2. And what about my numbers on the inside? Yep.
2, -4, 0, and 3.
Right. Don't forget the 0 because you're missing the x. You're missing the linear term. So 2, -4, 0, 3. Okay, so let's go through and let's do it. Okay. What's the first step when you do synthetic division?
Bring the first one down,
Bring the first number down. Okay, so we got 2.
then multiply it by 2.
Yep, multiply it by the number on the outside. So 2 times 2 gives me 4. And where do I put that? Onto the -4. Okay, and what do we do with that column? Add it up.
0,
And we're going to keep repeating that until we're done. So 2 times 0 gives me 0. Add the column up.
0,
0. And then 2 times 0 again. And 3. Okay. So now we've got everything that we need to find the quotient, the remainder, and the EBA. Okay, let's start with the quotient. Okay, how do you write the quotient? Yep.
would it just be 2x squared?
Yeah, 2x squared. The quotient is not an equation. It's a term, or it could be more than one term. The only reason this is only a single term is because we had a 0 here and a 0 here. But the quotient is 2x squared plus 0x plus 0. We just don't need the zeros. Okay, how about my remainder? Yeah, the remainder is 3. Remainder is always the number all the way over on the right-hand side when you're done. And when you are doing synthetic division, the remainder is always just a number. If the remainder was more complicated than a number, then that means you wouldn't have had x minus something here. And you can't use synthetic division anyway. Okay. So that's the remainder. And how about the EBA? How do I have to write the EBA? Yep,
It has to be an equation.
has to be an equation, yes.
So we set it equal to
That's think they know how we're going to write the EBA? You could put f of x, yep, or what else could you put?
y.
Y, yep, either way.
Y equals 2x squared.
Y equals 2x squared. That's the EBA.
Is it always going to be y?
Or f of x. Yes. You could do it either way. That's it. It's the quotient, the remainder, and the EBA. Okay. Any questions on how we found those 3 things? Okay. So I want to talk about a couple points regarding EBM and EBA. First of all, they're not the same thing. The EBM, that's what we talked about yesterday, that's easier to find. It's just the highest degree term in the top divided by the highest degree term in the bottom. The EBA, that takes a little bit longer to find. That's when you do long division or synthetic division, and you look at the quotient. So there's two different methods for finding it. Any question on the difference between the methods? Now, if you find both the EBM and the EBA, it is possible they could come out the same, or they could come out different. If we go back and look at our problem, what was the highest degree term in the top of f of x? Yep.
2x cubed.
2x cubed. And what was the highest degree term in the bottom? Yep, x. If we simplify 2x cubed divided by x, what do we get?
2x squared.
Right, we get 2x squared. That would be the EBM. It did come out the same as the EBA in this one. But the only reason that the EBM and the EBA came out the same is because that came out to a 0 and that came out to a 0. If those hadn't been zeros, then the EBA would have been a little more complicated. We would have had some more terms there. And they wouldn't have matched. The EBM and the EBA wouldn't have matched. Usually these both don't come out to zeros, which means the EBA would be different than the EBM. But in this case, it wasn't. Any question on it? All right. Now, up until today, we've talked about two kinds of asymptotes. What are the two kinds we've talked about? Yep, Julie?
Vertical and horizontal.
Vertical and horizontal. Well, think about this one for a second. That's an asymptote. Y equals 2x squared. If you graph that, is it a vertical line? No. Is it a horizontal line?
No.
No. What is it?
Parabola.
It's a parabola. So this is an asymptote that curves. We're going to draw a picture of that in a second and take a look at it. You can only get asymptotes that curve when the degree in the top is bigger than the bottom. If the degree in the top is equal to or smaller, I worked hard to make those passes. Hey, you just threw it away. So when the degree in the top is less than or equal to the degree of the denominator, you will always have the kind of asymptotes we dealt with yesterday. Those are straight line asymptotes, vertical and horizontal. Now we're getting into problems where the degree in the numerator can be bigger. And if you look at the difference between the degrees, that tells you how complicated of an asymptote you're going to have. What was the degree, the biggest degree in the top of f of x?
2x cubed.
That's the term. So what's the degree itself?
Oh, 3.
3. What's the biggest degree in the bottom? 1. What's the difference between a 3 and a 1? 2. That's why the EBA had an exponent of 2. The further apart the degrees, the more complicated the problem gets. So if the top was like a degree 7 and the bottom was a degree 2, that's a difference of 5. That could be an asymptote that has a degree 5 to it. Okay. Degree 5 can take many more twists and turns than a degree 2. Okay, so the bigger the difference, the more complicated the problem is going to get. In general, we'll be looking at problems that have at most a 2-degree difference. And you wouldn't have to graph one like this. I am going to have you graph one with a 1-degree difference. But I would ask you to do the long division and find the EBA. Okay, so you do need to know how to find it. Yep.
Can you clarify what you mean by if not asymptotes can be curved?
So before we've had lines like this, and the graph gets like closer and closer and closer to something that was straight. In a minute, we're going to draw something that the graph gets closer and closer to, but the thing it gets closer to is going to curve. So this black dotted thing, this is going to become a curve, that dotted line. Okay. So the dotted line that I drew isn't going to be a line anymore. It's going to be like a dotted curve. And we're going to graph it right now on the calculator so you can see it. Yeah.
What does a degree 5 asymptote look like?
Well, if you had the worst, most complicated case, a degree 5 can turn 4 times. So 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So degree 5 could have something like that. Generally, the important part of the asymptote is just what's over here and what's over there. It's the two ends. Because remember, we're dealing with end. So it might turn in the middle, but these turns in the middle, even though it makes it more complicated, we actually wouldn't even care about them. Right? But let's do the one we just came up with. Okay, so let's graph the original problem, and then let's graph 2x squared. Okay, so in parentheses, we've got 2x cubed minus 4x squared plus 3 divided by x minus 2. Okay, is there a number that we are not allowed to plug in for x? 2, yeah, because that would cause you to divide by 0. So what are we going to have at 2 in the graph?
Horizontal asymptote. Vertical asymptote.
Vertical asymptote. Yeah, we're going to have a vertical asymptote at 2 because that would cause us to divide by 0. So let's just start with this. We're going to have to zoom out to see the whole thing, but we're going to see half of it. That's half the graph. And here's your vertical asymptote at 2. It's right there. Let's zoom further up and to the right. So let's set, actually maybe we don't even need to go to the right. Let's just set the y max at like 50. Okay, so that's the part you were seeing before, and you're going to see another part right around there.
Ooh.
Okay. So let's look at that. Okay, so there is your graph. Vertical asymptote is right here.
Oh, is that the?
That's the vertical. So this is a graph that wants to be a parabola because the difference between the top and the bottom, a 3 and a 1, is a 2. So it wants to be a parabola, but it can't because there's a value that causes you to divide by 0. So it's kind of like somebody had to cut the parabola at 2 and bend part of it down and then bend the other part of it up. Okay? So it can't connect. If you block the middle out, then it would look pretty much exactly like a parabola. So if I go like, just go like this. Okay, if you don't look at the middle part, it is a parabola, but something weird happens in the middle because of the dividing by 0 at 2. And what parabola does it look like? It's going to look exactly like this parabola. So let's graph 2x squared. And then compare that to what we have right there. 2x squared. So now, let's take a look at that graph. And I want you to compare the red graph and the blue graph, not in the middle, okay, but on the ends. So just ignore the middle and look at the ends. How do the red and the blue graph compare?
Very similar.
Yeah, they're very similar. They're almost identical. And that's exactly what the EVA does. It gives you a picture of what the ends are going to look like. And the formula is a much simpler thing to analyze than the original problem. Okay. What the EBA doesn't do is tell you what it looks like in the middle. And you can see in the middle, the red and the blue one don't look the same at all. Okay. But that's not what the EBA does. So the EBA shows you what the ends of the graph are going to look like. And if you notice, people see how the red and the blue are getting closer and closer together? The red is our asymptote. The blue is our graph. And as we keep continuing on, they get closer and closer. So if I was going to draw it like a real asymptote, I would have made the red one dotted. So if you want to see it dotted like we normally would do, I could make it dotted.
Did you have to like take a class on how to use a graphic calculator? What?
No, I guess I just learned over time.
That's crazy.
Yeah. So now it's done.
Yeah, dude, because I don't know how to do that.
So you can, it's a little harder to see on the left because they're so close, they almost look like they're on top of each other, but remember, they're not. They're just getting really close. But on the right, you can see it a little better. The red and the blue are getting closer and closer. So that's what a curved asymptote looks like. Any main question on how to draw it on the calculator or how to find it using synthetic division? Okay. So we already did example 6. That was use a graphing calculator to basically prove that what you found for the EDA matches the graph, and it did. So we're fine. All right, let's do one more where we find a quadratic EDA. If I want it to be quadratic, that means I need the difference between the top and the bottom degrees to be how much? 2. I need the difference to be a 2. So I could do like a 5 in the top and a 3 in the bottom. I could do a 9 in the top and a 7 in the bottom. But I've got to do something that has a difference of 2. Just so we can use synthetic division again, I'm going to do a 3 in the top and a degree 1 in the bottom. Yeah.
Is the denominator ever larger than the numerator?
Well, that's the kind we did yesterday.
Okay.
So yes, it can be, but that leads to horizontals and verticals. Today, the horizontals are gone. All right, let's find the EBA. So let's do 2x cubed minus 3x squared plus 6x minus 4. And let's divide by x plus 2. Okay, what's the degree, the highest degree in the top?
3.
3, and in the bottom?
1.
1, and the difference?
2.
2. So we are going to get a graph that looks like a parabola, but it can't connect because what number would you be able to plug in for x and you divide by 0? -2. So at -2, it's like the parabola is going to get cut. Part of it's going to get bent down, and the other part gets bent up. Okay, can we do synthetic division on this one?
Yes.
We can. We just have to be careful. What number goes on the outside? -2. Okay, and the numbers on the inside?
2, -3, -6, -4.
Not negative
2, -3,
6.
Oh,
Positive
+6.
6. -4. Okay. So let's bring down the 2. What's -2 times 2?
-4.
And then -3 plus -4
-7.
times -2.
-14.
Positive 14 plus 6, 20. And what's 20 times -2? -40. I don't really care about the remainder, so we only care about the quotient. So how would you write the EBA? Yep.
1 equals 2x squared. That's it.
This one.
There's 1. There.
Yeah.
Y. Oh.
No, you go.
Y equals 2x squared minus 7x plus 1.
Plus 20. Yep.
So you have to do the full.
Yeah.
Okay.
The whole quotient, yes.
He just didn't do it before.
That's your EBA.
Again.
Now, let's say they asked for the EBM separate. What's the highest degree term in the top?
3.
And what's the whole term?
2x to cubed.
2x cubed. And what's the term with the highest degree in the bottom?
X.
What would be the EBM?
2x.
That's the EBM. This time, the EBM and the EBA are not the same thing. All right, so let me type this in. So we've got 2x cubed minus 3x squared plus 6x minus 4. And I'm going to divide that by x plus 2. Okay, so first thing I'm going to do is just find a window that fits that. I'm going to try the window we had before, and if I need to adjust it, I can. Okay, this time I'm seeing the right half. I'm missing the left half. So it's probably higher up, because I can't see it. So let's set the Ymax to, let's try like 150. And see if we get the piece on the left side. There it is.
I have a field trip on that I need to decide.
Yeah, can you come back like at 12? I'll be on. Yeah, thank you. So now you can kind of see the look of the parabola. You can't see it going far down. If you want to see it dropping down a little bit lower at the vertical asymptote, you could set the y min lower. But you can see the overall parabola shape. Now, if you graph the EBA, it should follow along right here. And it should follow along exactly right there. If it doesn't, then we didn't find the right EBA. So, well, let's try 2x squared, because that's what we said at first. If you just put in 2x squared, you can see what's happening. Are they getting closer and closer?
No.
No, they're diverging. They're getting further and further apart. That's not the right EBA. So if we modify it and then put in minus 7x plus 20, and now graph it, it should look like they're getting extremely close, both on the left and the right side. Perfect. Yep. So that graph in red is predicting what the ends look like. Notice it's not really accurate at the beginning. It gets more and more accurate the further on you go. Any question on finding the EBA there? Okay. All right, so okay, let's try this one. This time we are going to sketch it by hand too. What's the degree in the top here? And what's the degree of that? What's the degree in the bottom?
1.
1. What's the difference between a 2 and a 1? 1. So this is going to be a degree 1 asymptote. Not as complicated as degree 2, but also not as simple as a horizontal. Anybody have a guess what degree 1 is going to look like?
Would it just be a straight line?
Well, it's going to be a line, but what kind of line? Yeah.
Well, would it just have a break in it?
The asymptote itself, though, what kind of line will it be? No, parabola is a curve. That's not a line. This one won't be a parabola. Because you don't have a difference of 2. You only have a difference of 1. Yeah?
Will it be diagonal?
It's going to be diagonal, yes. So this time we're going to have an asymptote. That's what we call a slant asymptote. It's going to be on a diagonal. It's going to look just like y equals mx plus b. That's going to be your asymptote. Okay, so let's find it. Can we use synthetic division?
Yes.
Yep. What would go on the outside?
3.
3. And the inside?
1, 4.
Bring down the 1. 3 times 1.
3.
And 4 plus 3. 7. 3 times. This is just to get the remainder. We'll just finish it. But what's 3 times 7? 21. And what's negative 1 plus 21? 20. Okay, so we've got our quotient, we've got our remainder. The part that we care about for the EBA is just the quotient. How would you write your EBA here? Yeah.
Would it be x plus 7 or x squared plus 7x?
X plus 7.
And so how would we write it as an EBA?
Y equals x plus 7.
Y equals, think of something, you have to write something you could type in that it would look like on the calculator. So it'd be like y equals x plus 7. So that's an EBA. The other thing they want us to find is the vertical asymptotes. What would cause you to divide by 0?
3.
3. So how would you write your vertical asymptote?
3. Or x equals 3.
X equals 3. Let's graph that. Okay, vertical asymptote at x equals 3. We're just going to put in a vertical line. Y equals x plus 7. What's the y-intercept? 7. So 1, 2, 3, 4. You know what though? Let's go by 2's on the y-axis, because if we don't, we're not going to have enough room to see the graph. So we'll go by 2's. That doesn't affect x equals 3. I can leave that right where it is. So we're going to be at 7. And what's my slope? 1 over 1. So up 1, right 1. But remember, I'm going by 2's. So go up to 8 and right 1. Up to 9, right 1. So that's what your line is going to look like. Right? And I'm going to just do the rest with a dotted line. Okay, so that is our slant asymptote. That's pretty good. And what we get in this case is almost like an X shape with the asymptotes, and it's in 4 sections. We're going to end up drawing in 2 of them. So let's put that in, and now we're going to use the table. Okay, so we got x squared plus 4x minus 1. So x squared plus 4x minus 1. And what was the bottom? X minus 3. All right, well, we know when you type in 3, you get an error, okay, and that's what should happen. What would be a good value we should check? This now goes back to what we did yesterday. Yeah?
3.001.
3.001, and we're at over 200,000. So just to the right of 3, okay, we're going to be way up there. What would be another good value to pick? Yeah.
Or 2.9999.
Right, so 2.999, and when we do that, we're down at negative 20,000. So it's very far down. Way down there. Okay, so we know what's happening on each side of the asymptote. We need a few more points, kind of x values in this section. What would be some good x values we could do? All right, we could do negative 2. Yep, what else?
2.
2, yep, we can do 2.
And 0.
Do 0. Let's do a few more further away.
Negative 10.
Negative 10. Okay, so let's do those. So graph them. We've got negative 2, 1. So negative 2. Remember, my y-axis goes by 2. So we're at 2, negative 11. So 2, negative 2, 4, 6, 8, 10, 11. 0, we're at a third. So just a little bit up there. And negative 10, we're at negative 4.5. So negative 10, 1, 2, 3, 4.
You're counting, but you have to.
Yeah, I gotta go by 2. So 2, 4, probably closer to there. That's better. Okay, so we can start to see what's happening in this section. It's gonna come up. It's gonna curve. And it's gonna get closer and closer to that slant as we keep going. And then what would be some other good x values to check on the right side of the purple line?
4.
Okay, so we can do 4.
10.
4 is going to go off my graph, so it's a little too high. 5 I can manage because I can go up to 20. That's okay. So 5, and then you said 10. 10 we can do too. So at 5, I'm at 22. So 1, 2, 3, 4, 5. That's 20. 22 would be like just off the graph. And then 10, we're at 20. Okay, so what's going to happen here, this is going to kind of come down, do something. It must come down a little bit. Let me fix that a little bit. Let's get one more point in there. So remember, this point is supposed to be like way up at infinity. That one's up very high. So it's going to come down. It's going to start to curve and do something like that. And it's going to get closer and closer to that slant.
4 is at 5.
4 is at 5?
Oh, no, you're putting, never mind.
Yeah, I did. I can't do 4 because it would be up too high. All right, so let's hit, set the Y max. We don't need 150. I'm only going to 20. So I'm probably not really going to see much on my graph if I only go to 20. Let's go to 40. And then I think you'll see the top part, bottom part, everything should look good. Okay, that's the piece in the lower left, and that's the piece in the upper right. And slant was x plus 7. There you go. So you're going to get closer and closer to that in each direction. Any question on that? Well, let me write this down first. So that asymptote that we just did in the last example, that's a slant asymptote. Any questions on that? Okay, so the last one we're going to look at, we're not going to sketch by hand, just on the calculator. And I just want to see what that graph looks like. What kind of asymptote, what kind of degree asymptote should we be expecting here for the EDA?
First degree.
First degree, right? That's y equals mx plus b. That's a slanted asymptote. So let's put it in, and we're going to start with zoom 6 and see what we've got. 2x to the 4th plus 7x cubed plus 7x squared plus 2x. And we're going to divide that by x cubed minus x plus 50. So divided by x cubed minus x plus 50. Let's start with zoom 6 and see what we got. Okay. Does that look like a complete graph? What do you think?
It could be a little better.
Yeah, what can't we see here that we mentioned we should be able to have in this problem? What kind of asymptote did we say we had? first degree, which is a slant. Well, I can't really see the slant at all. Like if you had a slant asymptote, I mean, if it was getting closer and closer to this piece up here, it would look something like that. But does that look like it's getting closer and closer to this piece over here? No, it has to be the same line. But if I was going to draw one like this, I might do it like that. These two don't even look the same right now. So what do you think we have to do to get a better picture of this? Yeah, we need to zoom out. So let's go a little bit more to the left and down. And that's going to show us the lower left a little bit better. Okay, I definitely can see the slant there. Okay, at least on the lower left part. Let's draw an asymptote and see if it matches up with the upper right. If I was going to put in an asymptote, it would probably be about like that. Now they're getting closer and closer together. Does that look like it matches up with anything it's getting closer and closer to in the top part? No. So the only thing that can happen is this piece needs to start bending back, like back down a little bit. If it keeps continuing up straight, it's not going to line up with that asymptote at all. So let's go up a little bit higher into the right, and then see if we can
If you
determine.
do a window of the X min and the Y min is both -40, you'll see the whole thing.
You see the whole thing?
Yeah. You'll see it bent out.
And we gotta. So you mean positive 40?
Yeah.
Yeah. So yeah, let's go higher on the X max. Now we could try positive 40, and hopefully we start to see it bend back. And we're yes. So we're definitely starting to see it bend back. Right. That's looking better. I don't think I need to go quite that much, but I am going to go a little higher on the Y. Let's see what that looks like. Okay, good. So now let's look at that. Let's see if we can put a line in that looks like it's getting closer and closer to. How does that look? Does that look like we can see the slant now? Yeah. So this is a good window for seeing the whole graph, right? That's a good window. These aren't the only values, but those are the ones I used for that. But is there anything here that we might need to actually zoom in on to check out a little bit closer? So zooming out gave us kind of the big picture, which is good. But I think there's something else we need to check out a little closer. Yeah?
Can you cross with a slanted?
Like, is it a vertical?
You can cross the slant, like we actually do right here.
Yeah.
So yeah, you can cross it. There is a vertical, yep. There's definitely a vertical asymptote somewhere in here. We'd have to set the denominator equal to 0 to find it, so we're not going to do that. But anything else that I might want to check out a little closer? That you can't really get the full story about looking at that picture. Yeah?
Any holes?
So this one, I will tell you, I don't think has any holes in it. So that'd get a little complicated if we had to figure that out, because you'd have to be able to factor the numerator, and that would be could be pretty tough on this one. So there are no holes, but what else could we check out a little closer? It's definitely something we've talked about before. Line graphs. Let me go back to Zoom 6. Maybe that'll help. Definitely something there we have to check out closer that I can't tell from that view. And it's even worse in this view. Yeah?
Is it x-intercept?
Right. We should look and see if we have any x-intercepts. Okay? We can't really tell by looking at this graph if there are any. It just looks like the bottom is completely flat. At least to me, it looks flat. So what could we set from the standard window, what could we set our Y min and max to if we wanted to, say, zoom in on that part right there? Yeah?
Max is 1, minimum is -1.
Yeah, let's try doing that. So let's set the max. I'm also going to set the X min to -4. I'm going to set the X max to 3. Y min, what did you say for Y min?
1 or -1.
-1 and 1. So we're going to make this box right here now take up the whole screen. And let's see what that looks like. Okay, so let's take this, put that there. And now we took this and blew that up to be the whole thing. What do you think we still need to do? Yeah, I think we need to zoom in even more. So now let's make the whole screen just that. Let's zoom into that area. What could I do for a Y min and max this time?
-0.0 and positive.
I think 0.2.
Yeah, I would negative. I mean, if you go like 0.01, that might be a little too zoomed in. But you could do a half, or I heard 0.2. I think 0.1 is going to work pretty good. So we're going to zoom in 10 times as much. -0.1 to 0.1. And let's see what that looks like. Okay, so look at what's going on here. What originally looked completely flat, when you zoom in, you started to see a little bit that it's not flat. And when you zoom in even more, you can see it's not flat at all. So how many times does that graph cross the x-axis? 4 times. 1, 2, 3, 4. 4 times. So when the directions here say find a complete graph, I would say you need this window to get the big picture and be able to see the slant, but you also need this to be able to see the x-intercepts. So I think you need 2 windows to really get a good picture here.
To check for x-intercepts, if it had one, couldn't you also do the calculate intersect?
If you wanted to find them all? Yeah.
If you wanted to just see if there was one, without zooming in.
Well, the problem is if you don't zoom in, let's say there were 30 x-intercepts in there.
Yeah.
You may find one of them. I don't know how you'd find all 30 because you'd never be able to move your cursor precise enough to get left, right, and guess. Here you can. I could put my cursor left, right, guess on all of them, but I wouldn't even know to look for more than 2 or 3 unless I zoomed in enough to see them. But yeah, you probably could find one of them, 2 of them. Yep. So any questions on the 2 different windows that we used? Okay, so always keep that in mind when you're graphing. Make sure you zoom out enough or zoom in enough to see things that could be hidden. Yes?
Do you think there will be ones like this on the test? Really
Well, I'm not, like what?
like questions like this on the test where you go really zoom in?
Well, if I ask you for x-intercepts and you can't tell if it's crossing the x-axis, then yeah, you got to zoom in until you can see.
Only if you ask.
Do we have to zoom in this much? I mean, that was a lot of zooming in. We usually don't have to do that much. But whenever something looks extremely flat, if somebody said, how many times does it cross the x-axis, I can't tell from that. If they didn't ask me about x-intercepts or a complete graph, then I would say no. You wouldn't need to zoom in there because they didn't ask for a complete graph. But I did. I wanted a complete graph. So that means you got to show everything that's important. And these are important. Don't make them feel left out. They're important. Okay. So that is the homework for tonight. So it's page 235, 40, 41, 45 to 47, and 51 to 55. Okay, just a reminder, I'll be after school tomorrow. We'll have a review day after we go over the homework. And the review will cover everything
gotta
that's
redo
going to
it.
be on the test.
Yeah, you got it.